All right, guys, let's revisit our lab just so that we can understand what was really going on. So the question was, how does force affect the acceleration of a system? Our independent variable is the force, our dependent variable is the acceleration, and we're going to keep the total mass constant. And our apparatus looked like this. We had a cart that was being pulled by this hanging mass because there was a force that was pulling on this hanging mass. That was the force of gravity. So how do we set up our lab, or how do we set up our tests? What is our independent variable? Well, say if each of these masses was 0.02 kilograms for a total, all of these together would weigh 0.06 kilograms. What's the force that we're actually applying to this system? Well, we know this formula. You can recognize this formula. The force of gravity equals mass times the acceleration due to gravity, little g. Let's just call little g 10 meters per second squared, just to make our math easier. So if we have a mass of 0.06 kilograms, what force is that applying to the system? Well, it's applying the force of gravity to the system. So I could figure out our first independent variable that I'd want to test, this test that's happening right here, by just kind of plugging in these values into our equation. 0.06 kilograms times 10 meters per second squared equals a force of gravity of about 0.6 newtons. Okay, so if you were to set up your chart, force measured in newtons, acceleration measured in meters per second squared, and you'd have your chart. Your first independent variable that you tested was 0.6 newtons by having mass that you're hanging from the string. And say you get a acceleration of, let's say, 0.8 meters per second squared. Okay, so this thing's accelerating, not accelerating too fast. Now, the next data point that you want to collect, the next independent variable that you're going to test, well, say you add another mass here. Well, where are you going to get that mass from? Because you want to keep the mass of the whole system constant, you're going to use a mass from here and add it. So do you see what I did there? I took a mass off the cart and I put that on the hanging mass. And so I kept the total mass constant, but I've increased the force. I've increased the force down here because now we have 1, 2, 3, 4 of these 0.02 kilogram masses. And so now my total mass here, all of these together, is 0.08 kilograms. And if I were to plug this in to this formula, to my force due to gravity equals mass times gravity, well, I'll get 0.8 newtons. So that's my second data point. And then we used our motion sensors. We collected data. We found the slope of a velocity versus time graph, and say we found that the slope of that velocity versus time graph was about 1 meters per second squared. And then you'd plot your data. You'd do 5 data points and you'd plot your data, and you'd get a linear relationship, acceleration on the y-axis and force on the x-axis. Remember, independent variable, dependent variable. Now, the other experiment, how does mass affect the acceleration of the system? Now we want to keep the force constant, but we want to change the mass, and our dependent variable is still the acceleration. So this one makes some sense to us. So we know that the force due to gravity equals the mass of that object times the acceleration due to gravity. Well, say that this mass here was around 200 grams or 0.2 kilograms, a little bit more than those little brass masses. This is 0.2 kilograms, not 0.02. Now, we have some masses here on the cart. We have some masses, say this is like 1 kilogram. This one here is 0.5 kilograms. This one here, it's the same as that one. That's going to be a 0.2 kilogram mass. And the cart, we'll say that's 1 kilogram. Now, what's the force on this system? The force on this system is 0.2 kilograms times 10 meters per second squared equals 2 newtons. This is going to stay constant for the entire experiment. We're only going to change the mass. So when we set up our chart, we have mass measured in kilograms, and we have acceleration measured in meters per second squared. And we kind of have a chart. And our first mass that we test, is it this 0.2? Is it these ones that are on the cart, or is it the whole system? Well, we've been talking about the whole system. So how does mass of a system affect the acceleration of a system? So that would be 1 kilogram plus 1 kilogram plus 0.5 kilograms plus 0.2. Let me do this really quickly. 0.2 plus 0.2 is 0.4 plus 0.5 is 0.9 plus 1 is 1.9 plus another 1 is 2.9. So we have 2.9 kilograms of mass to start, and say this thing accelerated at 1 meters per second squared. And then our next data point, we added another mass. Say we added, let's say we added a 0.5 kilograms of mass to the cart. We added it. So we're changing the mass of the system. And now we have 3.4 kilograms. 3.4 kilograms. And we find that the acceleration is 0.8 meters per second. Interesting. So we start to see a different trend. And you'll probably, if this was our graph down here, of acceleration measured in meters per second, always have your squared, always have your units, and force, mass is measured in kilograms. What would this relation, oh man, you can't see. What would this relationship look like? Well, it would be an inverse relationship. So a good question to ask yourself is how, looking at the direct relationship and the inverse relationship, how then were we able in class to derive Newton's second law from this experiment? How were we able to figure out that A equals F over A? How were we able to put F in the numerator and, F over M? How were we able to put force in the numerator and mass in the denominator? How could we have figured that out by just looking at our data? And that's a question to think about tonight. Until next time.